You know that little lock icon you look for in your browser? Ever wonder what's really going on behind the scenes? Well, today we're going to dive into the super clever system that keeps your private information safe online. It's truly the unsung hero of internet security, and you use it every single day, probably without even realizing it.
So let me ask you something. When you see that lock, when you connect to your bank or your email, what's actually doing the work? Is it RSA? Is it AES? What's the secret sauce that's protecting your data? And the answer, which might surprise you, is it's not just one. Nope. The security of the modern internet actually relies on a team effort, a really powerful combination of different tools all working together in what we call a hybrid system.
Okay, so to really get why we need this hybrid approach, you first have to understand this fundamental challenge in cryptography. It's a classic dilemma, right? We need our communication to be both incredibly trustworthy and incredibly fast. And as you're about to see, those two things are often fighting against each other.
Essentially, we've got two main tools in our encryption toolbox. On one side, there's asymmetric cryptography, things like RSA. It's absolutely fantastic for establishing trust. The problem? It's a real workhorse, requires a lot of processing power, which makes it super slow. Then, on the other side, you've got symmetric cryptography, like AES. This one is lightning fast. I mean, it can encrypt data in a blink. But, and it's a big but, it has a major weakness. Both you and the server need to have the same secret key before you can even start talking.
So, let's play this out. What would happen if we just tried to rely only on the trustworthy but, really slow method?
And that's a perfectly logical question, right? I mean, if asymmetric encryption is so great at creating trust, why don't we just use it for everything, all the time? Just go all in on the secure one. Well, this chart says it all. It's the problem in a nutshell. Look at the difference. Asymmetric RSA is just worlds slower than symmetric AES. If you try to use RSA to encrypt, say, a video stream or download a big file, your internet would just grind to a halt. It would be unusable. So for the bulk of our data, it's just not practical at all.
All right, so using the slow method for everything is out. What about the flip side? Let's just use the fast one, symmetric encryption. What could possibly go wrong there?
Well, this brings us to the Achilles heel of any symmetric-only system, the key exchange problem. Remember, to use that super fast encryption, you and the server both need the exact same secret key. But how do you get that key to the server safely in the first place? You can't just send it in an email, right? Anyone could just grab it. It's that classic chicken and egg problem. You need a secure channel to share the key, but you need the key to create the secure channel.
So yeah, this is the million-dollar question. How do we solve this puzzle? How do we securely pass a secret over a totally open, untrusted network like the internet?
And this is where the magic happens. The solution is just so elegant and powerful, and it is the absolute foundation of modern web security. Instead of choosing one tool over the other, we use them both, letting each one do what it does best.
This is it. This is the core idea of hybrid cryptography, right here. We use that slow, heavyweight, trustworthy system for one tiny but absolutely critical job, to safely protect and share the secret key for the fast, efficient system.
It really is the perfect partnership. One system's strength perfectly covers for the other's weakness. The asymmetric system builds the trust we need to solve that key exchange problem, and then the symmetric system gives us the raw speed we need to solve the performance problem. It's beautiful.
So, what does this actually look like in practice? When your browser connects to a secure website. Let's walk through a quick, high-level view of this cryptographic handshake.
Okay, so it all starts with this handshake. First, the server sends over its public key. Second, your browser does its homework and verifies the server's identity to make sure it's legit. That's the trust part. Third, once that trust is confirmed, your browser and the server use that slow, secure system to create a brand new, one-time use secret key. And finally, for step 4, all your actual data, the web pages, the images, everything is encrypted with that new key using a super fast algorithm like AES. The slow, trust-building part is over in a flash, and the rest of your session is all about pure speed.
And look, this isn't just some abstract theory. This powerful combo of trust and speed is working all around you every single day, in technologies you use constantly without even thinking about it. Every single time you see that HTTPS lock in your browser, yep, that's hybrid cryptography at work. When you send a message on a secure app like Signal or WhatsApp, you guessed it, that's a hybrid system protecting your private conversation. Your VPN connection that keeps you safe on public Wi-Fi, secure file transfers, they all rely on this exact same fundamental principle. Use the slow one to set up a channel for the fast one.
And ultimately, that's the whole point. Without this clever balancing act, the internet as we know it just couldn't exist. We couldn't have secure online banking that was also fast and responsive. We couldn't have private messaging. Hybrid cryptography really does give us the best of both worlds, making our digital lives both safe and efficient.
So this system has served us incredibly well, but it leaves us with one last really important question to think about. As computing power just keeps exploding, especially with the rise of quantum computers that could threaten our current security methods, what's next? What does the next generation of hybrid cryptography look like? How are we going to keep balancing trust and speed to keep our secrets safe in the future?